Hello, we're Team 2, and this is our presentation on gearbox design. My name is Gilbert, this is Ricardo, Olazo, and Angel Mendoza. So gearboxes are very commonly found in many applications in our lives, and a lot of times we don't think about them, but they're very important. And one very important application of gearboxes is in controlling the tabletop surface of an MRI machine. MRI machines do not necessarily have to move the table in an accurate manner, but they do have to transmit a large load and so require quite a bit of torque. We are designing our gearbox to be able to transmit 2.5 horsepower at a minimum, produce a velocity reduction which is favorable. In this case, we want to reduce input speed of 1,000 RPM to 50 RPM. And finally, we have to consider certain conditions in our environment in order to create an accurate design. Here we see a couple examples of existing gearboxes in the market. The top three are gearboxes designed using spur and helical gearing. The bottom one incorporates a worm gear. The first three do not produce velocity reductions efficiently. They do have high transmission efficiencies, but require many more stages to produce a reduction. They also do have much more accuracy for motion control than a worm gear would have. But these benefits are really not something we're after in our design.
So for our design alternatives, we decided to take three different approaches. The first approach, we decided to look at spur gears. Now spur gears are very efficient, however they do not accomplish the required speed reduction. To make the actual speed reduction that we were looking for, the 20-to-1, we needed 6 different spur gears. They also are not very efficient when it comes to using them for a 90-degree angle. For the second approach, we decided to include bevel gears into our design. Now, the design was still the same. The only difference now is that a 90-degree transmission was much easier to achieve. However, this was still not efficient enough for us. For our last design, we tend to look at we looked at worm gears. Now, worm gears give you a low efficiency. However, efficiency is not really required for our design, but they do give you a higher velocity reduction. We were able to achieve the 20-to-1 velocity reduction by only using one set of worm gears. Because of the alignment of our input and output shaft, which was required to be in the same horizontal plane while keeping the 90-degree angle, we had to add 2 spur gears of the same size to keep the same output velocity. For the cost estimate, we looked at the Boston catalog for the gears, and we looked at the McMaster-Carr for the bearings. We still came up to a price of $118, which is less than the actual price out there for the similar mechanism, which is $200.
Here we have the schematic representation of our final design. It's a worm and a worm gear setup. Some of the features that our gearbox has is we are using ball bearings on the input shaft. On the intermediate shaft, we decided to use lower friction bearings. Another characteristic of our design is that we implement some holes on the base for appropriate clamping action of the gearbox. This gearbox is going to work with grease as a lubricant instead of oil due to the low temperature that is going to work on. Here we have the video of the simulation of our gearbox. On the input shaft, we have angular velocity relative to 20 with respect to the output shaft. Some other features are the case will be cast iron for more resistance to the weather conditions. For the conclusions, we make valid assumptions during our calculations. We were able to meet all the design criteria by using the AGMA procedures. We proved that we can design a gearbox that actually can work under these conditions. Thank you.